Yeah, now it is formed. Okay.
Yeah, okay. So,
One
welcome to
second.
this.
1 second, sir. Because live stream is not start. Yeah, yes, Satvik, you can start. Yeah, Sahil, you can start.
Yeah. So, welcome to the live session for week 7 and 8. So, we have one programming question for week 7 and one for week 8. So, let's start by understanding the problem statement and by understanding the test cases for week 7 question 1. So, there is a story given here. Let's read that. As part of the new Digital India initiative, the government has decided to replace its existing network of optical fiber cables connecting the capital cities with upgraded quality cables. The cost of this higher quality, low latency cable is quite high, and hence the main aim of this project is to plan the network in a way such that it minimizes the total length of the cable required to connect all the capital cities. Okay, so we have cities like this, and we have to connect all the capital cities with the minimum length possible. Okay, so the government surveys the land area considering factors like residential property, terrain, etc. Comes up with a graph depicting the possible tracks for digging trenches between every pair of cities for laying the cables. This graph G contains n vertices numbered from 1 to n, where every vertex represents a city, and m edges, where every edge u comma v represents a possible track for the trench to be dug connecting the cities u and v. The edge weight represents the length of the track. You, as the chief strategic officer of this project, have to come up with the total length of the cable required to build this network such that the trenches dug along these tracks connect all the cities with the least amount of cable. Okay, so basically, the question says that if you have in cities, and let's say you have a track, you have a track here, you have a track here. You have to connect uh, these in cities by using minimum amount of cable. Okay, you have to do this. So by forgetting the story behind this problem, what it says in mathematical or data structural form is you have a graph with n vertices and m edges, and you just have to calculate a new graph for a tree such that the sum of the edges of that tree, of this graph or tree, is minimum, right? So if you consider this, what comes in your mind is a MST, right? A minimum spanning tree. Okay, so week 7 is based on that only. So let's try to understand the input. Input is simple. You have t number of test cases. For each test case, you have two integers and n comma m. N is the number of cities, and n is the number of edges. And for each m lines, you have three integers u, v, w, where u and v represent cities and w represent the weight between them. Okay, so this is what the input is. You have the constraints. So as I have said before, constraints are very important to note, because whatever algorithm you use to solve the problem will take some time, right? This will take some time. That time you have to calculate the time, and that should be, let's say, if the time limit is given to be 1 seconds, then 10 power 8 operations, maximum 10 power 8 operations could be done. So you have to design an algorithm in such a way that that it takes lesser than equal to 10 power 8 operations. Okay. So for this, you need to take a look at the constraints. Okay. Take a look at the constraints. Okay. So in this problem statement, we have the constraints. Okay. So let's say the max value of t is 100, the max value of n is 500, and obviously m is the number of edges. The max value is of order n square. N square. Okay. So now we know that we are going to run an algorithm which is related to MST. Okay, which is we have to find the MST, right? And here we will solve this problem using Kruskal algorithm. Okay, Kruskal algorithm, and we should know that Kruskal algorithm takes m log m time. M log n time. I will show you how. So if it takes m log n time, then it is n square log of n square. Order of this is order of 2n square log n. This is certainly lesser than equal 10 power 8 operations. If I assume that the time limit is 1 second, okay, I'm assuming the time limit is 1 second. That is the maximum number of operations that can be done is 10 power 8. So if n is given as 500, so this will be around 2 into 25 into 10 power 4 into log 500. So this is around 5 into 10 power 5 into log 500. So this is obviously lesser than equal to 10 power 8. Okay. So we can certainly apply Kruskal algorithm, okay, because this will not exceed the time limit. Okay. So now we know that we will apply the Kruskal algorithm. How we will do this? Let's understand. So we will consider this example. We have two test cases. We will consider only the first, and we will try to see what happens. Okay, let's see. So we have 5 and 6, 5 comma 6, that is number of cities are 5 and the number of edges are 6. So n is 5, edges, number of edges are 6. So 1, 2, 3, 4, 5. We have 5 cities. Let's see the edges. 1, 2, 6. So that means there is a edge here with weight 6. We have 2, 3, 5. Okay. So we have a 2, 3 with weight 5. Then we have 3, 4, 4. So that is 3 to 4 and the weight is 4. We have 1, 4, 1. So that is, we have an edge between 1 and 4 and the weight is 1. We have 1, 3, 2 and 3, 5, 3. So 1, 3, 2 and 3, 5, 3. So that is, we have edge between 1 to 3 with a weight of 2. And we have edge between 3 to 5 with a weight of 3. Okay. Okay. So this is the graph we have. Okay. This is the graph we have. Now what we will do, we will run the Kruskal algorithm. Okay. Kruskal algorithm. What the Kruskal algorithm does is, we have u comma v comma w. Okay. We have m u comma v comma w triplets. So what Kruskal does is, it sorts all the triplets based on the weight, based on their weight, increasing order, in increasing order, and will one by one try to pick u comma v comma w in the MST in the MST in the MST. Okay, so this is uh, this this is what the Kruskal algorithm does. Okay, so why is it sorting? It is sorting because we want to create a minimum spanning tree. Okay, this is a minimum spanning tree. So we want the length of the cable to be the minimum. Okay, so that is why we try to take those edges which have the minimum weight. Okay, so that is why we are sorting. And after we are sorted, we have U, V, W pairs. We try to pick this one, we try to pick this one in this order. And like we try to pick, right? We try to pick. So on what basis? On what basis? On what basis we select U, V, H, which has W weight, and add it to our MST. Okay. So on what basis we will do this? So let's understand what do you mean by a MST? What is an MST? It is a minimum spanning tree, right? What do you mean by tree? Tree is just a graph with no cycles. Okay, with no cycles. So you have one, you have two, you have three. This is a tree. Yes. 1, 2, 3. This is this a tree? No, it is not tree because it is a cycle. Okay. This is what is tree. And we have to, then what this minimum word represents is that the edges, the sum of weights of edges of that tree, of this tree, should be the minimum. Okay. This is what an MST is. Okay. So what we will do, for each U comma V comma W triplet, we will check if by adding U comma V edge to our MST creates a cycle or not. Creates a cycle or not. If it doesn't, we add this to our MST. Otherwise, we don't add it. Okay. So I think it is clear. And we're not checking about the weight because already we have sorted the triplets based on the weight in increasing order, right? So we just need to check that by adding the UVH, whether it will create a cycle or not. If it does not create a cycle, we will add this, and if it creates a cycle, we will not add. Okay. So this is what the algorithm is all about. So let's diagram this on this one. Okay. So what we will do, let's say, so first we will sort all the edges on the basis of the weight. So we will have 1,14. So this is the weight and this is U and V. Okay. Then we have 2,13. Then we have 3,35. Then we have 4,34. Then we have 5,23. And we have 6,12. Okay. So we have sorted. Now what we will do, we will pick this one, pick this edge, and we will check whether by adding this edge we are creating a cycle or not in MST. So let's say this is a resulting MST. Initially we don't have any edge in the MST, so what we will do, we will add 1 and 4, which has a weight 1. Okay, we will add that. So we are done with this. Now we will check 1 and 3. So by adding 1 and 3, we are not creating a cycle, so we will do that. Weight 2. So we're done with this. Now 3 and 5, we will add 3 and 5 because it does not create a cycle. We're done with this. Now for 3 and 4, if we add 3 and 4, if we add an edge between 3 and 4, it will create a cycle. So we will not do that. Okay. We will not do that. Okay, so we are done with this. We are not selecting this edge. Now 2 and 3. 2 and 3. If we add 2 and 3, we will not create a cycle. So we'll add it with weight 5. We're done with this. And if we try to add the edge between 1 to 2, we will create a cycle. That is why we will not do that. So this edge is also not selected. So this final, this is the resulting MST, final MST. So if we add on what comes out to be the weight 5 plus 3 plus 2 plus 1. So this is the summation of weights of all the edges of the MST. So the output should be 11, right? Let's check what is the output. It is 11 indeed. Okay. So we have understood what the Kruskal algorithm is all about. So like if anyone has any doubts, you can ask, or we will move on with the code. Okay. Yeah. Okay. So one more thing, like yeah. So when like what are we doing for checking? So let's say we want to add UV edge to the minimum spanning tree. So we will add it only if it does not create a cycle, and we will not add it if it creates a cycle. So how will we know if this will create a cycle or not? So for that we will use a disjoint set union data structure. Okay. So let's say we have the minimum spanning tree for now is 1, 2, 1, 2, and 3. This is the minimum spanning tree. That means this means that in the disjoint set union, we have 1, 2, 3 in the same set. So if we'll now try to add an edge between 1 and 3, what it does, the disjoint set union says that 1 and 3 belong to the same set. So because they belong to the same set, and if you try to add an edge between them, it will create a cycle. Okay. So we just need to check if V and U belong to the same set or not. Okay. For detecting a cycle. If it belongs to the same set, that means it will create a cycle. That means we will not add it. If it does not belong to the same set, that means we can add this edge in the graph because it will not create a cycle. Okay. So for Kruskal algorithm, a prerequisite is DSU. So in previous weeks, I've explained the code and actually it means. So I'm not going to explain that again. It is simple. You can go to the previous live sessions and look at it. Okay. So we'll jump onto the code now. So we're starting the code from here. So we are taking t test cases as input. For each test case, we are taking n and m. N is the number of cities, number of vertices, and m are the number of edges. Okay. Now we will obviously make a graph. So for each edge, we are having int u comma v comma w. That is, u and v have an edge between them with the edge weight of w. Okay, and we are pushing that in the graph. Now we call the Kruskal MST function. So we'll go here. So this is the Kruskal MST function. Okay, this is the main function. How are we doing this? So what we are doing first, we are sorting u comma v comma w triplets on the basis of w. So what we are doing, we are creating a triplet of w comma u comma v, and we are sorting this. So actually we are creating a pair. What is a pair? W comma u comma v. So this is a pair. Okay, and we are sorting this pair. We're sorting this pair on the basis of w. Okay, till here it is clear, I hope. Now this one is disjoint set unit data structure. Okay, this one disjoint set unit data structure. We are initializing b equal to 0. This part is disjoint set union. So uh, for each for each edge u comma v comma w, what we are doing, we are checking if u and v belong to the same set or not by using a DSU data structure. Okay, if they are present in the same set, if they are present in the same set, so like what DSU does is, if you have u and if you have v, you find the parent of u, you find the parent of v. If the parent of u and parent of v are equal, that means they're in the same set. If they're not equal, that means they are not in the same set. Okay, so if parent of u and parent of v in the same set, that means we can't add an edge between u and v, because it will create a cycle. Okay, and if they are not, then we will add u and v. What we will do, we will add u edge between u and v in the set, and we will add the weight of this edge to our final answer. Okay, and now like if you are saying some if else statements which consists of rank and parent of v method, so what it is basically, so we have u, we have parent of u, we have v, we have parent of v. What we do, we find the rank of parent of u, we find the rank of parent of v. If parent of u and parent of v are not equal, then we will check the rank of these two, and based on the ranks of these two, we will combine the we'll combine the sets containing u and v. Let's say if we have this as one component, and if we have, let's say, this as another component, and if we try to add an edge between, let's say, 2 and 6, what we will do, find the parent of 2, it is 1, find the parent of 6, it is 4, they are not equal. So what we will do, we will attach 4 to 1. So in this way, we have combined the component 1 and component 2 into a single component C, and we have seen the ranks of 1 and ranks of 4, and based on the ranks we are doing this. I will not go into the details of how we are attaching. You can see in the previous live sessions where I've explained the complete DSU. Okay, so in this way we are doing, and yeah, so then we are returning the answer. Okay, so this is what is all about Kruskal algorithm, and we have solved the question. I hope everyone understands it. Let's now move on to week 8 question. Okay, so week 8 is based on max flow, and this is a like standard question for this. Let's understand the question well. So what it says, that we have a source and we have a sink. Given a directed flow network where each edge has a capacity of flow it could allow, find the maximum flow over the network from source S to sink T, and we have to follow these rules. The first rule is only one source and only one sink is there. Other than the source and sink, nodes are represented with alphabets A to O. There are no self loops. There will be no initial dead ends other than T. For any pair of nodes, direction of edges between them will be in single direction. Okay, so we need to follow these rules, and based on these rules, we will like obviously the question will have the input given in a way that it follows these rules, and by reading the input, we will form a graph. Okay, let's understand the input. The first line contains an integer e, the number of edges. In the next e lines follow. Each line of the next e lines contains 3 values u, v, and w, denoting that there is a directed edge from u to v. having a capacity of W. Okay. So the constraints are given here. I'm not going into the detail of the time complexity of this algorithm because like the algorithm which I will tell you, it will be satisfied. It will be under the time limit. Okay. And the final output should be a single integer indicating the max flow from the source S to the source to the sink T. Okay. So let's look at this test case. What do we have? We have a source S, we have a sink T. From S to A, there is a flow with capacity 8. From S to B, there is a flow with capacity 10. From A to B, there is a flow with capacity 4. From A to C, there is a flow with capacity 8. From A to D, there is a flow with capacity 5. A to D is 5. B to D is 2. B to C is 5. C to D is 3. C to T is 4. And D to T is 12. Okay. So this is our graph. Now the numbers are representing capacity of the flow. Okay. So from S to A, maximum flow that can exist is 8. Okay. Maximum it is 8. It cannot exceed 8. Okay. So we need to understand that. Okay. So now let's and for this graph we need to find the max flow. How will we do that? We will run the Ford-Fulkerson algorithm. Okay. So what this algorithm says, let's look at it. There are some terms which I will use repeatedly, which is bottleneck capacity, residual graph, and augmenting path. Okay. So the algorithm says that for each residual graph, find an augmenting path with the bottleneck capacity. Sorry, find an augmenting path by noting down the bottleneck capacity of this path and add this bottleneck to our final answer, which is the max flow. Okay, so this is the algorithm. So we need to understand what a residual graph is, what an augmenting path means, and what does the bottleneck capacity mean. Okay, so let's understand by running the Ford-Fulkerson algorithm on this graph. So we have S, we have T, we have a here, we have a B here, we have a C here, we have a D here. This is 8, this is 8, this is 10. This is 4, this is 2, this is 5, this is 5, this is 12, I guess. This is 3 and this is 4. So this is the graph. This is a graph. Okay, you need to understand this is a graph. Now graph is also a residual graph. Okay, you need to understand it. Understand this graph. The initial graph is also a residual graph. So we will have many residual graphs. We will have many residual graphs. Out of those many residual graphs, the initial graph is one of those. Okay. So what we will do from this particular graph, from this particular graph, and this graph is a residual graph. So from this particular residual graph, we will find an augmenting path. We'll find an augmenting path. What do you mean by a augmenting path? That means you start from source S, and if you are able to reach till T by following any path, this path is called as an augmenting path. Okay, and we will have the bottleneck capacity of this path. So what do you mean bottleneck capacity? Let's say we have a bottle like this. So you have so much of water filled here, but the amount of water that can spill out of this bottle is only this much. This is the bottleneck. Okay, so this is what the concept is. For example, you have source, you have T, you have A, you have B, and you have T. This is, let's say, an augmenting path. You start from S, you reach S. Let's say the flow from S to A is 4, the capacity. This is 3 and this is 7. So what is the maximum flow? What is the maximum flow that we can get from S to T? It is 3, right? Because the capacity of this is 4, the capacity of this is 3, the capacity of this is 7. But the flow, maximum flow which we can get is 3. Okay. This is the bottleneck. The bottleneck is the minimum of all the capacities of that augmenting path. Okay. So I hope everyone understands what do you mean by bottleneck capacity. So we have understood all the terms. We have understood what a residual graph is, what an augmenting path is, and what a bottleneck capacity is. Now we will jump onto the algorithm. Let's do it step by step. Again, I will have to make the graph. Okay. S is there, A is there, C is there, B is there, D is there, E is there. This is 4, this is 2, and this is 3 and this is 4. Okay. Yeah, so I hope I have drawn the graph correctly. Let's verify again. 8, 8, 4, 10, 5, 5, 2, 3, 12. Okay. Yeah. So this is the initial graph, and this is also a residual graph. Okay. Now for this residual graph, we will find an augmenting path. What can be an augmenting path? You start from here, you reach here. From here, you go till here. From here, you go to this. This is an augmenting path, right? Yes, this is an augmenting path. So an augmenting path we have is S to A to C to T, 8, 8, and 4. What is the bottleneck capacity? Bottleneck capacity is minimum of all the capacities. It is equal to 4. Okay. Now we have found the augmenting path. We have also found the bottleneck capacity. What we will now do, we will add this bottleneck capacity to our max flow, which was initialized to 0. So now it is 4. This will be our final answer. Okay. This is 4. Now what changes we will make onto the residual graph? What changes we will make? So for example, from U to V, if the capacity was C and if the bottleneck was B, then what we will do? we will change this one to U to V C minus B. So the now, so like what we have done, we have, let's say water is flowing from U to V. So we have flown B amount of water from U to V, which had a capacity of C. So now the capacity of U to V is C minus B, and we add a reverse edge from V to U, which will have a capacity B. Okay, so this is the change which we do in the graph. Okay, so this will be the change which we will do in this residual graph. So what happens is, so this was 4. So what we will do, we will add a reverse edge, which will have the capacity as 4, and this edge will become 4 minus 4, which is equal to 0. So we will remove this edge. It like, we will not remove this edge, but like obviously the capacity of this edge will become 0. The capacity of this edge will become 4, and we will add a reverse edge, which will have capacity of 4. We add a reverse edge, the capacity of 4, and this reduces to 4, and everything else remains exactly the same. Okay, so now the graph looks like this. So this is a lengthy algorithm. You guys need to have patience. This is 4. This is 4. This is 4. This is 4. This is 0. And this is 4. 12. This is 10. This is 3. This is 5. This is A to C is 4 and C to D is 2. Okay, so now this again is a residual graph. We will again find a augmenting path for this one. So the augmenting path will be, the augmenting path can be, let's say, start from S, you go till A, you go to B, you go to D, and you go to T. Okay, so this can be an augmenting path. The bottleneck, so S to A to B to D to T. We have 4, we have 3, and then we have 12. So the bottleneck capacity becomes minimum of these, which is 3. Okay. So now again we will do the same thing, that we will add a reverse edge with the bottleneck capacity 3, and we will subtract this one. 12 minus 3 becomes 9, and we'll do the same thing here, here, and here. So the resultant residual graph is as follows. So let me mention that I'm running the algorithm. It will take time because there are many augmenting paths, 4 to 5, I guess. This was the second one. And yeah, I forgot one thing, that we add the bottleneck capacitor to max flow. So this is now 4 plus 3, 7. Okay. So the max flow till now it is, for now, is 7. So what happens to our graph? We have a S, we have a A, we have a B, we have a C. Sorry. So this is C and this is B. Okay. So what changes will we make? This is 9. The reverse is 3. This is 0. This is 4. This is again. This is 7. This is 7. This is 1. This is 1. This is 10. This is 2. This is 4. This is 5. This one is also 5. And from C to D we have, so this is 0 and the reverse one is 3. Okay. So now again this is a residual graph. We will find augmenting path for this. So the augmenting path can be, let's see. So to start from S, you go till A. From A you reach D, and from D you go to T. So this is an augmenting path, S to A to D to T. Okay. This is 1, this is 5, this is 9. So the bottleneck capacity is the minimum of 1 comma 5 comma 9, so it is equal to 1. Okay, we will add this 1 to our max flow, so max flow becomes 7 plus 1, which is 8. Okay. It becomes 8. We will make the changes to our residual graph. The changes will be as follows. So I hope everyone is getting used to this algorithm. You have a residual graph, you find the augmenting path, you find the bottleneck capacity, you add that bottleneck capacity to the max flow variable. You again you do the required changes. You again like repeat all these steps till you don't find an augmenting path in the graph. Okay, so we are going to reach that situation. Let's have patience. Yeah, so this becomes 8, this becomes 0. So now we cannot have any water flowing from S to A. Okay, so this is interesting. This also becomes 0. This is 4. This is 4. This is 10. This is 4. This is 2. Now this becomes 8 and this becomes 4. And let's say from B to C we have 5. So B to oh sorry. From B to C we have 5. From C to D we have nothing, with 0. From D to C we have 3. And from A to D we have 4 still. And from D to A it is 1. It's so yeah, like the graph is becoming a little bit messy, but let's have patience and understand. So now we need to find another augmenting path. You start from S. Now see, you cannot go to A. You cannot go to A because the capacity is 0. Okay, so you start from S. You go to B. You go to B, and from here where can we move? We can go to D, and then we can go to T. So this is augmenting path S to B to D to T. So this is 10, 2, and 8. The bottleneck capacity is equal to 2. You add this bottleneck capacity to the maximum flow, which becomes 8 plus 2, which is 10 now. Okay. Now we again have the residual graph. We will make the changes. So the changes as follows. So let's make the changes here only. Okay. So this is okay. So this becomes 8. We add a reverse edge to 2. This becomes 0. We add a reverse edge to 2. And this becomes 6, and we have 6 here. Okay. So now this is the residual graph. This is the residual graph. We need to find an augmenting path in this again. Okay. So what will be the augmenting path? Let's see. Let's see. We start from S. We go to B. We go to B. We cannot go to D because the capacity is 0. So we go to C. We go to C. From here, let's say we go to A. Then from A we go to D, and from D we go to T. Okay. So the augmenting path will be you start from S, you go to B, then you go to C, then you go to A, then you go to D, then you go to T. Okay. And the capacities are as follows. Capacities are capacity are 8, 5, 8, 4. Okay, so this is 8, this is 5, this is 8, this is 4, 8, 4, and from D to T it is 6. Okay, this is 6. The bottleneck capacity is nothing but minimum of these, which is equal to which is equal to 4. Okay, 4. So you add it to the max flow is 10 plus 4, which becomes 14. Okay, this becomes 14. Now again you make the residual graph. Okay, so let's do the changes here only. Let's make a new one. Let's make a new one. So this is A. Sorry. This is S. This is P. This is A. This is B. This is C. This is D. Okay. You have here. You have here. Okay. And all the reverse edges, let's say, identify by this thing. The reverse edges. The reverse edges. Pencil is not working. The pencil is not working. I don't know why. There's some problem here. Hmm. The pencil is not working. Just a second.
Sahil, can you close this this editor and reopen again? Then check.
Yeah, guys. So it's working now. Just a second. Yeah, sorry for this. Yeah, so where was I? Like we were making the residual graph. So from S to A, we have 0. This is 0. This is 0.
Sahil, your screen is not visible.
Yeah. So I hope it is visible now. So this was 8. This was 8. This is 4. Okay. This becomes 2. This becomes 10. Yeah. So from 8 minus 4. So this becomes 4. This becomes 6. From B to D, we had, okay. So this is 0. This is 2. From A to B, we have 4. From A to D, so from A to D, from B to C, we will have 1. And we'll reverse this by adding a reverse edge with the capacity 4. From A to D, what was the bottleneck capacity? Yeah. So from A to D, we have 0. And from D to A, we have 5. Okay. So now again, we need to find an augmenting path, right? Augmenting path. So let's try to find augmenting path. From S, we can't go to A. Okay, so this is not possible. From S, we can go to B. We can go to B. Now from B, we can't go to A. We can't go to D. We can go to C. So we reach C. From C, we can't go to T, right? We can't go to T. So the capacity from C to D is also 0. Okay, and from D to C is 3. Okay, so from C, we can't go to D. We can't go to T. From C, we can go to A. Now from A, we can't go to B. That will make a repetition, right? So this is not allowed. Repetition is not allowed. And from A, we can't go to S, we can't go to C, we can't go to B. We also can't go to D because the capacity is 0 here. Okay. So now we are stuck at A. From S, we went to B, we went to C, we went to A. Now from A, we can't go anywhere. That means we no longer have an augmenting path. No longer have an augmenting path. That means the graph which we have got is the final residual graph, and we no longer can get any other residual graph. So the max flow for this graph is equal to, what was it, 14. So it is 14. Okay. So let's check the answer if it is correct or not. Yeah. So if you see, the output is 14. Okay. So we have run the Ford-Fulkerson algorithm successfully. So I guess we had made 5 residual graphs, 5 augmenting paths, and we found the answer. Okay. So this is what we do on paper. Let's see what happens in the code. Okay. This is one function, and sorry. This is another function. Okay. So let's start from the main function. What we are doing, we are creating a graph. Okay, we are creating a graph. We have a 2D graph. 2D graph. We have vertices from A to T. We have from A to T, and the box represents the graph of UV, represents the flow from U to V, the maximum capacity from U to V. Okay. So in this way, we are creating the graph and we're calling the Ford-Fulkerson function. So this is the function. This is the function. What it takes the source, which is S, sync, which is T, and the graph. Now we have a parent array. The concept of parent array is very important. We have a parent array. So we have a parent array which has A, B, C up till we have a D up till S and then D. Okay, and everyone is -1. What does -1 mean? That we are initializing this with -1. That means we have not reached A from somewhere. We have not reached B from somewhere. We have not reached G from somewhere. Okay, that is what -1 means. And let's say if we remove -1 and -1. Let's say if we remove -1 from here and we add B, that means we have reached T from B. There is a direct connection from B to T. So the parent of T is B. Okay. So this is what is the importance of the parent array. So initially everyone is -1. Okay. We have the residual graph, which is equal to the graph, and then we have the max flow. The max flow, which will return finally, and then we have the min capacity. Min capacity is nothing but the bottleneck capacity. Okay, it is nothing but the min capacity is nothing but the bottleneck capacity. Okay, so now we find the bottleneck capacity by calling a BFS function. Okay, so what algorithm was, we have a residual graph, we find an augmenting path and the bottleneck capacity of this augmenting path. Okay, so we'll find the bottleneck, we'll find the augmenting path by using the BFS algorithm. How will we do? See, so this is the BFS we are doing. Okay, so we are initializing the parent array with -1. We have the size of the residual graph. The source of the source is initialized to -2. So the source element in the parent is initialized to -2. We have a pair. We have a queue. Obviously, as we have it in a BFS, we have a queue. And initially, we are pushing in the queue a pair of source comma infinity. Okay, so this infinity tells about the capacity, which we are going to return. Okay, so this is the second element will tell about the capacities. Initially, it is infinity. We have to find the min capacity. That is why we initialized it to infinity. Now, until the queue is empty, what we are doing, we take the first element of the pair, we take the second element of the pair, and we pop from the queue. So we'll pop S comma Q, U is equal to S, and the capacity is infinity. Okay, use infinity. And what we'll do now, we'll traverse through all the vertices of the graph. Which are the vertices? A, B, C, D, S, and T. We'll traverse to all the vertices one by one, and we will check these conditions, that if the parent of vertex should be -1, that means that it should not be reached by someone else. And obviously, if we are going to reach from U to AV, the parent of U should be -1. The capacity between U and AV should not be equal to 0, right? If these conditions are met, then we enter the if condition and we say that the parent of AV is equal to U. The minimum capacity becomes the minimum of the capacity and the capacity between this edge. Okay. And if we reach the sink, if we reach T, then we'll return the minimum capacity. Otherwise, we push AV with the minimum capacity. Okay. So how are we doing this? Let's understand. So this is what we do. This is what we do, and finally, like, we return the minimum capacity. Okay. So this is the BFS algorithm to find the augmenting path and the bottleneck capacity. Okay. We return the bottleneck capacity. We add it to the max flow, and now we do the required changes. In the residual graph. Okay. So how are we doing the required changes? So let's say if we had the graph like this. The pencil is getting disconnected again and again. I don't know why. It's not working again. Yeah, so like I don't know why the pencil is not working. So let's leave it like we are, like, obviously we're like anyway they're going to end. So what happens is, so for this one, this thing, like, we are making the changes. So while we were finding the augmenting path, we found the augmenting path by using the BFS algorithm, right? So by, like, we have the path. Okay, we have the path. So what we will do, we will traverse this path in the reverse order. We will traverse the path in the reverse order in this while loop, and we'll do the required changes in the residual graph. Okay. So I hope everyone understands this. It is quite easy. We will travel it like so. Initialized U is initialized to sink, right? And while we have not reached the source, we travel in the opposite direction and we do the required changes. Okay. So in this way, we will update the residual graph, and again we will find an augmenting path. We'll find the minimum, the bottleneck capacity of that path, and we will add that bottleneck capacity to our max flow variable and we'll return the max flow. Okay. So in this way, we run the Ford-Fulkerson algorithm on paper, and then, like, we have also written it down as code. So yeah, that's all. That's all for week 8. Sorry for the inconveniences. Again, my pencil is not working. I don't know why. I will fix this issue in the next live session. So yeah, that's all from my side for week 7 and week 8 programming questions. Now I request Satvik to please like explain the week 9 problem statement. Thank you.
Yeah, just give me a second. Okay, so all right. So this is the week 9 programming assignment question number 1. So what we are given is that there is a race with n competitors and there are m checkpoints in the race. So there are there are n racers and each racer can reach any of the m checkpoints. And but after a racer reaches a particular checkpoint, that checkpoint gets closed and is not open to any other racer. Right. This is a checkpoint and this is a racer. If it reaches, like, then the other racers cannot reach this one. Simple. That's what it says. And the race ends when K racers finish the race. Right. What this means is that when K racers, we are given n racers, out of that, if K racers reach any of the checkpoints, any K checkpoints, then our race ends. And now what we have to, okay, we are given that each racer travels at constant speed throughout the race, which might be different for different racers. Now, we have been given n racers and m checkpoints and speeds of each racer. What we have to determine is the minimum time needed to end the race. Right? End the race is like when K racers out of n racers reach K checkpoints. That is when the race ends. We have also defined the time required for racer at coordinate p comma q with speed s to reach a checkpoint x comma y by this formula. And okay, so just an example, if what this function means is that if, like, for example, 24/7, 25/4 is 6.25. If we take the ceiling, it would give us 7, right? So now this is the question. I guess pretty much it is clear what we have to do in this. Now we will be given 3 integers n, m, k, which will denote the number of races, the checkpoints, and the number of teams, minimum number of teams that have to complete in order to race to be completed. Then the next n line will indicate the coordinates of n races. The next m lines will have m checkpoints, and finally the speed of ith racer. Also, these are the constraints given to us, right? And okay, so let's start with, we can take an example input. We are given this input. In this input, we can see that n equals to 3, m equals to, yes, sorry, n equals to 2, m equals to 3, and k equals to 1. This means these are the total number of racers, right? These are the checkpoints, and this is the minimum number of races that I have to finish, right, in order to race to be completed. And then these are the coordinates for the two racers, that is 0, 1 and 0, 0. The next 3 lines are the checkpoints coordinates, right, that are 0, 10, 27, 29, and 458 and 9651, right? And finally, these are the speed of the races. This means that this racer travels with speed 5 equals to 5, and this one travels with speed equals to 3. Right. Now we have to determine what is the minimum time race finishes. Okay. So here k equals to 1. So only one racer needs to finish, reach any checkpoint. So if you see that, let's consider 0, 1 as a racer that for the, he finishes before 0, 0. So 0, 1 can go to 0, 10, 27, 29, 458, 9651. I'm not gonna calculate the time required for each. We'll just see that by observing, you can see, like, okay, what we have to, the formula for this one was p minus x square plus q minus y square, right? And this is s square, right? So if you consider 0, 1 racer, the racer at 0, 1. The speed is given to as 5. This means the base would be, denominator would be 25. And here would be p minus x, that is 0 minus x square and 1 minus y square, right? So if you just make you can just clearly look that 0, 10 would be the nearest one, right? You have to minimize the time. So just find the nearest checkpoint. The nearest checkpoint to 0, 1 would be 0, 10. You can put it into this formula and check it, right? So from 0, if you find the time, what would the time? The time would be this would be x would be 0 square plus 10 minus 1, 9 square upon 25, right? This is 81 upon 25, which is equal to 4, right? This is the time taken by 0, 1 to reach from 0, 1 to 0, 10, right? Time required is 4. And if you consider 0, 0, you would see that in order to reach from 0, 0 to any other checkpoint, the time would be greater than 4 only. You can check for 0, 10. For 0, 10, it would be 0 square plus 10 square upon its base is this 9 s square 3 square is equal to 9. Then this would be 100 upon 9. It's clearly greater than 4, right? So that is why the minimum time required is 4. The racer we are choosing is at 0, 1, and it is going to the checkpoint 0, 10, which speed equals to 5. So that is why this time is equal to 4. So this is the explanation for the question of week 9. And yep. So I guess that's it.
Yeah, okay, Satvik. So if you have any anyone, if you have any doubt in any question, you can ask in the Google forum or Discord forum. Okay, so we will meet in the next session. Thank you. Thanks, everyone.
Thank you, sir.
Yeah.